This first chapter in the textbook is all about logical thinking and formal logic, and how can we write down logic. So that's what we're going to look at first. Formal logic. For us programmers in the class, you'll be familiar with some of the logical connectives that we're going to talk about. And so you'll notice some of the things we talk about in this chapter are intended to help you with making sure your programs are logically sound. For us mathematicians, the reason we're talking about formal logic is so we can develop proof techniques. And the whole point of this class actually is to learn how to prove theorems. So this is kind of the foundation for all of that stuff. First, we need to know what a statement is. So we're going to define a proposition or a statement. Is a declarative sentence that is either true or false. But not both. So we're not doing any of those, the following sentence is false, true or false situations like that. So we're saying a statement is just something that's either true or false. So for example, the statement P could be the statement that Josh likes cake. That is either true or false. Or the statement Q could be Josh hates puppies. That is either true or false. What do you think it is?
Well, you should be more specific, because maybe you like chocolate cake, but you don't like vanilla cake.
It doesn't matter. It's still true or false. Yeah. What we're going to look at is how to connect statements like these with logic, so logical connectives. And then use those statements to represent theorems and to be able to formulate arguments. So the logical connectives that we're going to talk about are and, or, not, implies, and if, and only if. Which, to programming people, you should know those from just writing an if statement once in your life. The notation we're going to use for and is that, kind of a caret, or, just like that. Not, we're going to use either a tilde, or sometimes we use that symbol. Implies is an arrow. And then if and only if is an arrow going both ways. By the way, in LaTeX, I think the symbol for that is land and lore for logical and logical or. I think. You can Google it. This one's probably not. This one's right arrow. And that one's probably double arrow or something. I don't know. I'm pretty sure those are right though. And so, we're going to create these logical statements using these connectives and then discuss the truth or not truth of them. And the way we do that is by constructing these things called truth tables. Okay, so what a truth table does is it shows every possible scenario, essentially, of the truth value of the statements that are being used. So let's look at the truth values for and for or. So say we have two statements, P and Q. And I want to figure out the truth value for P and Q.
Are you just using like those letters like as
P and Q?
As they're like statements?
Yeah, P and Q represent statement. It's just tradition to use P and Q for stuff. Convention. But they do represent statements. So P and Q are some statements, and we're going to discuss the truth value of them. Now, when you're making a truth table, you have to fill out all possible truth values that a statement could have, all possible combinations. So the typical way to do that is like this. So the P is either be true or false. So I'm going to do true, true, false, false. And then Q can be true or false also. So true, false, true, false. And the way it's like, if you divide it in half like that, go down by a half each time, you get every possible combination. So true, 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 false, false, true, false, false. That's every possible combination of true and false you can have. We'll look at an example in a little bit where there's P, Q, and R, and then there's going to be more situations that could arise. Now, for P and Q to be true, what do you think has to be the case? So if P is true and Q is true, well then P and Q is true.
Yeah.
Right, so there we go. But if P is true, but Q is false, well then P and Q is not true, so that'd be false. And then that would also be false, and then this would also be false. So those are the truth values that could arise depending on what P and Q are.
So pretty much if it's not like two truths, it's false.
Right. For the AND logical connective. How about the OR logical connective? What would have to be the case for that to be true?
Would false have to be?
Well, so if both are true, is P or Q true?
As long as you have not
Yeah.
true, you're good.
As long as you have one true, then it's true. So this one being true means that OR is true. False and true means this is true, and then if both are false, then it's false.
Can you go over that like one more time? Please, thank
So for an OR statement to be true, at least one of the things has to be true. So just treating like either Josh likes cake or Josh hates puppies. If both of those situations are true, then the OR statement is true. Say that it's true that Josh likes cake, it's false that Josh hates puppies. Well, does Josh like cake or does Josh like puppies? Or Josh hate puppies? Yeah, Josh likes cake, so it's true. So for the OR, at least one of them has to be true.
you. So if there's any true value in there,
Then OR will be true. But for AND, both have to be true for the AND statement to be true.
Is there such thing as like an XOR statement?
You mean exclusive OR?
Yeah.
Yeah. There's more logical connectives than just these we'll get into. That would eliminate the first case then.
So what are these going to be labeled on here? Like class ones?
Oh, I'd usually label it by, I'll say like notes from January 9th.
Okay.
We can go and fit in another one over here. Let's do the negation. So the not. Let's do not P. So negation means you're going to take the opposite truth value from what you got. So if P is true, then not P is false. So not
So it's the opposite.
is the opposite truth value, yeah.
Okay.
So if P is true, then not P is false. Or if P is false, then not P would be true. That's what negation means.
How come you don't write like P and then little squiggle and then Q like this?
Well, these are binary. You're talking about two statements that you're connecting like that, but not just means it's the one statement is not true or false. Now the implies is a little bit tricky. So let's look at P. Well, so P and Q. Let me rewrite it. True, true. False, false. True, false. True, false. P implies Q. The way you can think about an implication statement is by saying if P, then Q. And this is going to be really important when we start developing theorems. You know, if 2 points are on a line, then what can be true about them? So let's think about that. So if P, then Q.
P is true and Q is true?
Uh huh.
That's true.
So then is this statement true?
Yes.
Yep. How about the if?
That's false.
Yep, that's false. Now these two are a little kind of tricky. These are true by default. We refer to this as being vacuously true. So the idea with that, if we look at this statement as an object by itself. If P, then Q. But we don't have this being true, then the entire statement we're just going to say is true by itself. We're not concluding Q is true, but the entire if-then statement is being said to be true, just kind of like by default. Okay? So when we're talking about these truth values right here, these aren't the truth values of Q. These are the truth values of the statement if P, then Q. So I'm not saying right here that Q is true. I'm saying that this statement is true. Maybe we give it some... so let's say if it's raining, then it's cold outside or something. So, well, we're saying if it's not raining, I can't conclude anything about the temperature outside because I don't have this first part of the implication. So what we're saying is by default, this entire statement is a true statement. It's called being vacuously true.
The order that you're writing these in, I mean, this would change depending on the statement, though, right? Like,
Oh yeah, the statements will get more complicated than
okay.
these.
So we're not always going to be true, false, true, true. It depends on...
It depends on what kind of thing you're proving or trying to show is logically equivalent.
Are we going to practice one of these?
Oh yeah. I'm just explaining what all these symbols were.
Can you
Right
define
now.
vacuously true for me, like written out?
Yeah, it's just like I like to use the word true by default or something.
I don't really understand how it's true by default.
Logically, I don't... Yeah.
It's sort of like you get a little understanding of what you're trying to say.
Well, so when you say it, you don't understand why it is true by default. What is your it referring to?
Like, hold on. Is that statement like if it's raining is P and then
Well, so
is Q?
raining is P and cold is Q, yeah. And so you have to think about P and Q separately first. So for the first row right here, it is raining, it is cold, so the statement, if it's raining then it's cold, is true. Right? For the second part, it's raining but it's not cold, so the statement, if it's raining then it's cold, is false. But down here, it's not raining. I can't really say anything about the implication statement. So over here we're saying, oh, it's just true by default. Because we don't have the first part of the implication. Okay?
So why wouldn't it be false?
Just by convention we choose it to be true.
It should be false though, because it's not raining.
Why?
That's what we're talking about. It's raining. When it's cold.
So you use the word it again. What is it referring to? It being cold outside?
No, it's it being P and Q.
So explain it again. But you're talking about it being cold outside would be false. But that we're not talking about it being cold or not the truth value. We're talking about the truth value of the statement, if it's raining, then it's cold.
Will it always be like P first, then Q next?
Or it can be different than that.
Then how can you tell the difference between a P and a Q in a sense?
I mean, the problem will say P represents the statement blah, Q represents the statement blah.
Okay, that's what we got to figure out.
Yeah. I think the hard part that you have to wrap around your head is that these truth values aren't talking about whether or not it's... We already know the truth values for P and Q. We're talking about the truth values of the whole sentence,
It's
if
not talking
then.
about whether or not it is or isn't cold because the other one.
Exactly.
It's talking about is the correlation itself.
Exactly. That's exactly it, yeah.
And so you can't prove it, you can't say it's wrong, so it's just that you choose to say it's true because
Right.
it's a default value.
Exactly. That's exactly right.
Why is that the default?
So,
This is what they
Because
do.
it's just the best answer we have because
so
we
if
can't
it's
prove
not
it. It's
raining, then it's cold? Would that be the one for the third statement?
If it's not raining, it's not cold.
What you're talking about, this line right here?
Like,
So,
if
it's not true that it's raining. It is true that it's cold. But since it's not true that it's raining, this implication doesn't have any logical meaning. So we're just saying true.
It's not proven false.
Yeah.
You're saying. So it has to be true because it's just not proven false right now.
I mean, I guess you could say that.
Who does... Okay.
Will it be the it's hard with numbers though.
Oh, there's no numbers in this class. Numbers? What are you talking about? Well, if you like that one, let's try the biconditional, the if and only if.
So this is curricularly just a theorem-based class.
Yeah.
Okay.
Could you use a different statement maybe? Maybe the raining and cold is not.
Yeah. Sure. Let's do that with this one.
Well, maybe just an easy example of what we will be doing in the class.
Oh, that's kind of... Well, you know what? How about we do one in the book in a second?
Okay.
Because that'd be right out of the class. Let's get through a little bit more of this, though. So, this, the if and only if, is called a biconditional. And I wish I didn't write the table like that. Because what this means is that P implies Q and Q implies P. So this statement is the same thing as P implies Q and Q implies P.
So does that mean it has to be true for both sides in order to be true?
In one situation, yeah. But let's look at it. So let's figure out what the truth values of this statement is. To figure out the truth values of that, though, we're going to figure out that guy, and then connect them. So let me draw the truth table again. So we got P, Q. We need to know P implies Q. We need to know Q implies P. And then we need to know the entire thing.
So when we're writing it out, we need to write it like this.
Right. Like if you're trying to figure out the truth values for a complicated logical statement, you're going to find like each piece individually and then connect them. So we got true, true, false, false, true, false, true, false. We just did P implies Q up here. That was true, false, true, true. All right, let's do Q implies P. So if Q is true and P is true, then this statement itself is true. If Q is false, then it's vacuously true. Right? If the first part is false, then it's just true by default. Okay? If Q is true and P is false, then this implication is false. And then if Q is false, that means it's vacuously true. Okay? So for an implication, if the first part is false, whatever comes in front, that means the implication itself is vacuously true. For an and, we said that means both of them have to be true. So both are true. This is true. Only one of them is true, so that's false. Only one of them is true, so that's false. But then both are true down here, so that's true. So this is the truth values for a biconditional if and only if statement. True, false, false, true.
Can you break it up and then put it together in like math terms, kind of with a little pivot thing?
Mm-hmm. But so far we haven't actually used these truth tables to prove anything or show anything. I'm just showing you how does a truth table work and how do these statements kind of work. I agree it's confusing.
Can you go over the last, how you got the last one again?
These two?
No. Yes. No. Farthest to the right.
This one.
Yeah.
Oh, an and statement means both of the things have to be true. So I just looked at both are true, then only one, so those are false, and then both are true, so it's true.
That's kind of like, that's like the first one. That's the same as the first one.
Mm-hmm. Okay. In addition to the implications, there's other ways we can make statements. So an implication is just what we said. P implies Q. If P, then Q. There's also something called a contrapositive, a converse, and an inverse. So a contrapositive, you're going to switch the sides and negate both. So the contrapositive is not Q implies not P. The converse, you just switch the sides. That would be Q implies P. And the inverse you just negate. So not P implies not Q. So these are special. I mean, you should be familiar with the vocabulary that we're using. So implication is an if-then statement, and then there's several different ways you can flip it around to get whatever you need. Let's give some words to this, though. So let's pick a statement for P. So P is going to be Crystal likes Starbucks.
So this is like words, like a word math class?
Yeah. I mean, aren't there words in every class?
Yeah, but like, I was expecting like kind of like algebra.
Oh, I mean, there's going to be some like numbers and functions eventually, but we're not going to be solving any equations or.
Is this more just about thinking logically?
Yeah.
Just teaching us how to think about math, basically.
Exactly. Yeah.
So we're not like learning, I mean, we're learning new stuff, but it's like breaking it down to.
Well, so what we're going to learn first in this class is how to think logically and how to prove theorems. And then we're going to look at special cases of things and then apply some of those logical techniques to it. So one of the first things we'll look at are functions, for example. Y'all remember functions, f of x equals blah, blah, blah. We're going to prove a theorem about a function and then show isomorphisms about the function and then do all this stuff with function. Or we're going to learn about graph theory, and for the computer science people, we'll learn search algorithms and stuff. And we're going to prove, like, okay, well, if the graph has so many nodes, then it's going to take so much time to get through the graph or something like that. So the first part is going to be a lot of logic and proving stuff, but then we're going to do very specific mathematical things and apply the logic to it. Anyway, let's look at this. So Crystal likes Starbucks, and Q is going to be
I like Chick-fil-A.
I don't know how to spell your name.
Just put Z.
Likes Chick-fil-A. Does Chick have a K in it?
Yeah.
It is like Chick with a. I don't know, right?
I don't see it in each other.
Look on your cup.
Yeah, have a game.
Okay.
Okay.
I mean, I don't know. Anyway, so implication, P implies Q, would be if Crystal likes Starbucks,
And then Z likes.
then Z likes Chick-fil-A.
You're totally other things.
But still, a logical statement exists regardless. Not Q implies not P would be that if Z does not like Chick-fil-A,
And Crystal doesn't like.
then Crystal doesn't like Starbucks.
So what about the inverse? If,
Well, converse is next.
do you have to do it in that order?
Well, no. But, I mean, I wrote it in that order. Might as well go in order. What would the converse be? Q implies P.
It just mean if Z likes Chick-fil-A, then Crystal likes
Starbucks.
Starbucks.
Right. And so Z likes Chick-fil-A, then Crystal likes Starbucks.
Where you wrote
No, he didn't. He said if Z does not like Chick-fil-A.
And then the last one would be if Crystal doesn't like Starbucks and then Z doesn't like Chick-fil-A.
Right.
I don't get it.
So Crystal doesn't like Starbucks. And Z doesn't like Chick-fil-A. Maybe that helps visualize what these things are intending to mean. Now, we're not concerned right now with the literal truth value. In fact, we're going to consider every possible truth value with these when we're making our truth tables. And one thing we're about to start figuring out is how can we show statements are logically equivalent? So which of these statements is actually saying the same thing?
The Q
top
implies
and
Q,
bottom.
and Q implies Q.
You think P implies Q and Q implies P mean the same thing?
No.
I don't think so, because P says if Crystal likes, then Z likes. But this one says if Z likes, then Crystal likes. So it changes the assumption that you're making.
So
For-
could it be the second and the third one?
These two?
Yeah.
So if Z does not like, if Z does like. Something to think about.
None of them,
Some of them do.
Who was it that said that the top
First
and
one.
bottom one? Yeah, I think that one's right.
So if Crystal likes Starbucks, if Crystal does not like Starbucks.
You can say both like on both.
We better draw some truth tables to figure this out. But before we do that, let's go to the textbook and work out some problems. So, just a little more practice. Does everyone have a textbook they can glance at?
Can you leave those on for a minute so I can finish writing?
Oh yeah. If you could go to page 10 in the textbook. Page 10 in the textbook has a few problems we can look at. Let's just start with number 1. So the statements, P is the statement, there is water in the cylinders, Q is the head gasket is blown, and R is the car will start. And so for part A on this one, it says, translate the following into logic symbols. So if the head gasket is blown and there's water in the cylinders, then the car won't start. Okay, so break that down for a second. So the big thing that you need to know is that it's an if-then statement, right? If blah, 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 then something happens. So we're going to have an implication. What should the first part of that be? If Q, so if the head gasket is blown, and there's water in the cylinders, so not just Q. Okay, continue.
Then the up arrow.
Yeah,
And E.
right? And then after the arrow, after the implication, the car won't start.
So squiggly.
Squiggly R.
Is there a technical term instead of squiggly?
Not. People just say not. Or the actual symbol is a tilde. And there you go. So if the head gasket is blown and there's water in the cylinders, then the car won't start. All right. How about part B of that? That starts in logic, and we have to go back to everyday English. So R implies.
If the car starts.
So if the car starts, yeah. If the car starts,
Then there isn't water in the cylinders.
then there's not, yeah. There is not water in cylinders, or the V thing is the or, right? Or, oh, sorry, Q isn't the, sorry. Well, I guess it doesn't matter what, yeah. So Q is, the head gasket is blown, so then the head, is it gasket?
Yeah.
Is not blown. Or there is not water in the cylinder. No, the not will go to both. Because it's in parentheses. Again, we're not concerned with truth values. That's just what the statement is. Cool. I think number 2 I put on your homework, but are y'all kind of okay with this?
So, for B, that little L-shaped thing.
Oh yeah, that's a not.
Okay, so that.
It's the same as the tilde.
So that goes to both of the
Mhm.
statements. It's like not like you distribute it.
There are some distributive rules we'll get to in a second, but yeah.
Translating and stuff like that, that's good.
Yeah, I think so. What about number 5?
What is, why'd you put the arrow on A with the squiggly?
The arrow is there because it's an if-then statement. Whenever you have if something, then something, you use the arrow for the implication. The squiggly is because it said it won't start.
So the squiggly is like one, not,
Right.
doesn't.
Yeah.
What is that little thing?
This thing?
Yeah, that's,
Same thing as the squiggly.
so you can write either one or do you write both?
I use the squiggly, but I guess the book uses the...
Why'd you write two?
I didn't.
You wrote both.
That's an R.
Oh. Okay, gotcha.
Number 5.
It looks just like that thing.
No, it is the other way.
But I thought you just wrote it wrong.
We're moving on. Number 5. If it's raining, then the ground is wet. So if it's raining, then the ground is wet. And first it says, but the converse. So what would the converse be? Go back and look at what the converse means.
The ground is wet.
It's red, then it's raining. Yeah, the ground is wet.
Yeah, so converse would be if the ground is wet, then, oh, I guess I should write then
Always
raining.
comes first, so Q is if it's raining and P is the ground is wet.
There's you just
Wait.
represent arguments. There's no
Yeah,
real
there's no-
order to the variables. It's just there to represent information.
Right. So in this problem, P is this and Q is this, and then it flipped.
But could it be like the ground is wet? Wait, if the ground is wet, then it's raining. That'd be Q and P.
No, so with the implication, whatever the first statement is, P and Q don't always have to go in a certain order. P just represents one thing and Q represents the other thing. So this statement is if the first thing, then the second thing. However is written in the sentence, whatever it gives you. And the converse is going to flip the order of those. What's the next part? The contrapositive of the statement.
So the converse is if the ground is wet, then it's raining.
So what would contrapositive be?
The ground is not wet.
The
It's
ground
not
is
raining.
not
Right. Yeah, ground is not wet, and it's not raining. Okay, so seems less scary.
Who comes up with this stuff? Like, who came up with this?
Mathematician.
Just
This,
mathematicians throughout
this
the
guy named Neil Boole, I believe.
I was really hoping you would say Neil Patrick Harris.
No. And programmers will understand Boolean operators.
Okay.
And they use this in philosophy too. If you ever take a philosophy class. Because they like to, find the meaning of life or something.
There is no meaning.
Let's look at those truth tables again and look at a problem like number 10. So number 10 says, use truth tables to establish the following logical equivalences. So this is one reason we like truth tables. If two statements are logically equivalent, it means the statements have the same truth values. So essentially, to show two things are logically equivalent, make a truth table and show that two of the columns are of the same thing, and all the same falses and trues. So for the first one, part A, we're going to try to show that not P or Q is the same thing. The symbol for logical equivalence is an equal sign, but with 3 equals bars. And it's logical equivalent to not P and not Q. So Zaire, this is the distributive rule that you had mentioned. And in fact, we're going to go back in a second and correct some of the language we were using. But let's do the truth table first. So we got to have a P. We got to have a Q. We're trying to show not P or Q, so we better have a P or Q column. Then we have to have a not P or Q column. So that's going to be like the first one right there. Then we got to have, we're trying to show this statement, so let's break it down into pieces. We got to have a not P, we got to have a not Q, and we have to have a not P and not Q. Okay, so our goal is going to be to show that the red column and the green column, they should end up with the same trues and falses in them. And that means it's logically equivalent. No matter what, it's the same truth values there. So you can break it up the same way. So P is going to be true, true, false, false. Q is going to go true, false, true, false.
So for the first two, those will always stay the same though?
Yep, that's just to give you every combination. Yeah.
Okay, that's all right.
You
If-
start that way every time?
Yeah, well, I mean, if there's more statements, then there's more rows,
Right.
but we'll show you that in a little bit.
But like same order.
hmm
Okay.
Always like break it up into half chunks, and it'll give you every combination. All right, P or Q. What's that mean again?
True.
Well, yeah, the first one's true, but how do I know?
Because
Yeah, at least one of them has to be true. So it's going to be true, 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 and then false. Okay. Not that.
True.
No, it's the opposite.
So that's false.
Yeah, false, 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 and then true. So not just means the opposite truth value. Okay, we got that one done. How about not P?
when we're finding these, do we look at like what we got?
Yeah,
All 4 of them?
that's the point of breaking it up into pieces so you can build up what you need. Because if you skip this part and try to figure out this without having that, it'd be kind of tricky. You have to be thinking a lot in your head. But if you break it up piece by piece, it's a little easier.
You can do it on like paper.
Right. So not P, I heard false.
False.
Yep.
True, true.
Yep. How about not Q?
False, true.
False, true, false, true. Not P and not Q. For and to work, both have to be true. So what's it going to be? Yep, false. And then true, because both are true. And hey, look at that.
What is that?
I have the same.
Oh, wow. Wait a second. So not P and not Q. Why wouldn't?
Go ahead.
Well, if you're saying where P is false and Q is false, wouldn't the top one be true?
No, we're looking to see when is this true, and it's only true if both are true.
Yeah.
If both are false, it's still false.
But okay, so you have where not P is true, so it's false, and not Q is true, it's false. So where they're both false, it should be true, right?
It should be true.
No, you're thinking of it like the implication thing,
Okay.
but this isn't a state. Like it's not.
So this is of the two statements next to it.
Yeah.
Okay.
So this whole shebang here is just to show that they're logically
Equivalent.
equivalent.
So this is equal to this.
Okay, cool. We just proved that. So yep, that's right.
Yeah. This is called De Morgan's laws.
So I guess it would be that one there.
That's just the name of this distribution rule.
This isn't relevant. Can I ask you this?
Yeah.
Okay, cool. So in mathematics, we have laws, but I notice in science they refer to a lot of things as theories. But surely gravity's not just a theory, right? It would be a law.
Well, yeah. When scientists use the word theory, they mean law.
So why
They're just
not?
being pedantic. In mathematics, we think of things more pure because we can prove everything entirely logically, and there's no holes in it.
Oh, but you cannot do that.
But scientists, they don't like to think that way. That's why they refer to things as theory.
Okay.
But I guess we're more arrogant.
As we should be.
What I was going to mention here is how to actually word this out loud, because we worded it incorrectly in that problem we did about the car and the gasket and everything. Where was that problem? Oh, it's on the back over here. So, where is it? Well, we did it. Oh, yeah. In the first, or the part B of that problem, this one, in the book it was R implies not Q or P. And I could tell you were a little concerned about how it was sounding because it wasn't right. So what this is telling us, if we have a not in front of an or like that, when it distributes, it's equivalent to saying not Q and not P. So if the car starts, then the head gasket is not blown and there's not water in the cylinders, with how we would say it out loud to be sound. And that should make sense too, right? Because if we say or, then if it's not an exclusive or kind of situation, then the car wouldn't start if there was still water in the cylinders or something. So Anyway, De Morgan's Law. Notice the part B of that one. What is that, number 10?
So you would say that like not P or Q logically equivalent to not P
And not Q. Yeah. These two are the exact same statement as each other.
but ordered different?
So it's like it's like saying, I do not want pizza or cake, which means I do not want pizza and I do not want cake.
Okay.
Of course, that's false. You guys want to try the next one? It's almost the same thing, but good practice. So not
We're on 7, right?
number 10 on page 11. So not P and Q.
Is that a little squiggly line?
Yeah. Is logically equivalent to not P or not Q. Okay, so it's almost the same thing. We go ahead and practice doing that. I'll pause it and let you try to fill out the truth table.
Yeah, will you give us like
I mean, same thing.
So you should have at least got the first two columns, right?
Is it hot? That's all you want to do?
Yeah, it is kind of hot in here. Is that
Yeah,
okay?
it is. I'm swimming.
You should have got P and Q next. That's what we're interested in developing this statement. So P and Q means both. So that should be true, false, false, false. And then not that. You should have got false, true, true, true. Just negate all those truth values. The next statement we're trying to develop is not P or not Q. So I made a column for each little piece of it. Not P would be just the opposite of those guys. Not Q would be the opposite of those guys. And then for the or statement, at least one of them has to be true. So you get false, true, true, true again. And that means they're logically equivalent.
Okay, so I just missed that.
So, when you say not P, that means.
That's where I'm at.
Like whatever P was, not that.
Because
Okay.
all of my others were
And whatever Q is,
so I missed
Not that. Yeah.
and that,
This
and
is
that
based off of this.
specific line or whatever.
Mm-hmm. Now I did want you to pay close attention to how these distributive rules are working. When a not distributes over an or, it turned into an and. And when the not distributes over an and, it turned into an or. So that's exactly what De Morgan's laws say about that. Oh.
I think we can do another one.
Yeah, let's do another one. I want to do one where there's more than just two letters. The next one I want to do is number 14 on page 12.
with numbers?
There's no numbers in this class. I guess the page number. Yeah. You can make tables in LaTeX, but it's kind of difficult.
So you're not required to do that.
No. For true tables, I'll let you write it out by hand.
I thought we didn't have homework tonight.
Your homework tonight is to figure out LaTeX and look at that document and
But you
stuff.
said number 2 was our homework.
Eventually, it's going to be.
Okay.
Right now, all I want you to do is learn about LaTeX. I can't give you too much on the first day.
Yeah.
I mean, goodness. I'm not evil.
Leave this.
But let's do number 14, though. So in number 14, we have P, Q, and R. P is the statement, Andy is hungry. Q is the refrigerator is empty. And R is Andy is mad. So the first part of that problem, we want to use connectives to translate this sentence into logic. So if Andy is hungry and the refrigerator is empty, then Andy is mad. So what would that be as a logical statement?
So P, caret, Q.
Go on.
Then an arrow,
Yeah?
R.
Yeah, that's right.
Oh.
Put it in parentheses just for being fancy. So if Andy's hungry and the refrigerator is empty, then Andy's mad. So there we go. Now it says construct a truth table for that statement. Okay. So when we're making a truth table for P, Q, and R, we're going to start with those, but we're going to have a lot more rows. How many rows will we have, in fact? 8.
How? Oh, yeah.
Because when we make this, we're going to divide it in half each time, like I said. So we're going to have true, 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 false, 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 false. And then
Oh, God.
true, true, false, false, true, true, false, false.
And then true, false, true, false, true.
Right. And that's just like a gimmick to make sure you get every combination that's possible. We want every combination of all the possible truth
Wait,
values.
why do you put so many?
Because you need every combination.
Why'd you put 8? Because there's going to be 8 rows?
hmm There's no other combinations we can have of 3 things chosen 2 at a time. How many rows would we have if there was 4 statements?
4 letters?
Yeah. 16.
Well, 16.
16.
How do you know it's gonna be 8?
What?
2 to the number of letters.
Oh, okay.
That's a statistics question, though. You should learn about that in counting. Oh, Maddie, you know what? We'll learn about that Thursday.
Yay. Is this going to having 2 math classes, am I going to be confused?
Not as much as Crystal and Corbin are.
What?
You guys have 3 math classes?
Oh, we're doing the algebra as well.
All right. To make this statement, we need P and Q. And then we need the whole thing. P and Q
Have you taken this stuff?
implies R. So for P and Q, and means that both has to be true. So what are the truth values going to be here?
You have that other one?
15 minutes after.
15 minutes is P and Q?
Totally, yeah, let's do
I think it should be true. What about this?
Yeah, that's true.
You're going too fast for me.
Hold on, so.
Yep. Ooh. Rewind.
So true, because they're all true.
I'm only looking at P and Q, though,
Oh, we're just looking at P and Q.
for this column here.
So true, false, 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 false. Yeah. Gotcha.
Okay. And then P and Q implies R. So if this is true and this is true, then the whole statement is
True.
true and false.
False.
False and true. Huh?
True.
Vacuously true, right? If the first part's false, then it's true by default. Oh, and that's going to be all the way down, right?
Why?
Because the rest of them are false.
What? Why is
Oh,
That was the vacuous thing.
Vacuously true, the first part isn't true, so you can't prove the rest of it.
And then the others are both false, so.
No, it doesn't even matter about the R. Once the first part of the implication is false, the implication is vacuously true.
how come you put
So this one was true because both were
Okay, I
true.
get it.
Okay, good.
I think so, maybe.
wait, can you explain again why there's only one false?
The only time this is false is when the first part is true, but the second part is false. So once this is true, this thing has to be true. That's what implication means. But that's not the scenario here in that row.
And for the ones that are both false, that makes it true.
Once the first part's false, it doesn't even matter what happens after. If the first part of the implication is false, then it's vacuously true.
Okay. Oh, okay, I got you, my bad.
And then part C says, suppose that the statement given in part A is true, and suppose also that Andy is not mad and the refrigerator is empty. Is Andy hungry?
Yes.
So we're going to say, it says this thing is supposed to be true. And we're also supposed that Andy's not mad, so that means what? Not R. And the refrigerator is empty, so Q. So this is true, this is true.
Whoa.
Is Andy hungry?
Why are you writing it like that?
I just didn't want to write out all the words.
So, Andy isn't mad. What does the T's mean?
True. This is what part C of the problem says. So the statement is true, and Andy's not mad, and the refrigerator is empty. Is Andy hungry? So what do we think?
I'll tell you in a
Okay.
minute.
Figure out where in the truth table we can be looking.
I have to catch up. Remember when you had me? You were mad because I took so long writing? I wrote every single thing down.
I'm going to post it after class.
Yeah, I'm not going to go home and look stuff.
Well, why write them down in the first place?
No, look online. I I don't like that. I like the Q and B thought.
Any ideas if Andy's hungry or not? You say he is hungry?
I mean,
Pretty sure options.
He's not.
He's not hungry?
Yes, I would be.
Well, let's see. We basically define the row in the truth table that matches this scenario. So if we know this statement's true, that means we're looking at one of these.
So,
And-
do we need to make a not,
R column.
yeah,
We could, or we could just figure out,
false, true, false, true.
right, we know what's going to be. So if this is the case, if not R is true, that means R has to be false. We're only looking at that row, and that row now.
And you missed the top one.
Oh, but I'm not looking at that one anyway,
Because
Oh,
that's
yeah.
because
false.
it didn't match the first scenario.
Okay, so Q
And
has to be
then
true?
Q has to be true, so that means we're looking at
That one?
this one,
That's it.
and that's it. So this is the row we're looking at.
Okay,
So is he hungry?
yes,
Why?
because P and Q,
P is Andy's hungry.
false.
Yeah, P is false, so
He's not hungry.
he's not hungry.
Well, because not R is supposed to be false. And we're looking for that.
No, not R is true, which means R is false.
Oh, yeah.
And Q is true,
We just
and the
found
whole thing was
false
true.
Under R,
Q is true.
can practically just match everything else.
Right.
I'm not gonna be a logical.
Why isn't it the one above it?
Wait, could you say that again?
Oh, never mind, I get it.
Okay.
It doesn't matter which one is false. They both have to be true. It's and.
wow, this is mind blowing.
Let me ask you a question. Do y'all want to take a break, or can we keep going?
If we take a break, if we don't take a break, can we get out early?
I guess.
Can I go get my first with our
Well, so we are going to take a break?
How do we get out?
I guess we are.
Like 4:30? Let's take a break. Just 5 minutes, though. We'll start at 3:40.